Okay, so this video is to help with scientific notation and calculating wave speed, wave frequency, and wavelength. So, scientific method is sort of a shorthand version for writing either really big or writing really small numbers. So, for example, what if I had the number 1250000000000? Now that might seem like a number you wouldn't use very often, but we use numbers bigger than this all the time in chemistry, say when we're talking about atoms. So you might have a lot of something that's very, very small. Or if you're talking about space and you have lots and lots of stars. So to keep writing this would be kind of annoying because this is a really big number, and if you're multiplying it and dividing it, you get really big or really small answers. So we try to have a shorter way of doing it, and it's going to follow the basic format. I'm going to use something like a dot a times 10 to the blank. So the idea is that you want to have some like 3-digit numbers here that are, for the most part, not zero, and you do times 10 to the whatever number you want to put up here. Now, let me show you how we would actually figure this out with the number that we have the example of. So, erase this. So 1, 2, 5, and all those zeros can be written in a form of shorthand. So what I want to do is look for the numbers that are not 0, which in this case is 1, 2, and 5. And I'm going to rewrite that as 1.25 times 10 to the. So I put my decimal point here. So now I have to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 times 10 to the 13th. So these two numbers mean the same thing. I could take the number 15000, 15,000, and rewrite it as 1.5 times 10 to the 1, 2, 3, 4, fourth. Okay, so writing really big numbers means that you're going to have, so if you're showing like a really big number, you're going to have a positive number here. So if I had even a number like, I don't know, 3,000 could be written as 3.0 times 10 to the third. So again, these two numbers are equal to each other. Okay, so let's do another example with a really small number. What if I have the number 0.0000000000575? Okay, so again, it's a really small number, and we can deal with these types of small numbers when we talk about wavelength of a wave, which is what we're going to do in this unit. So here I have to count. Again, I want to have that these three numbers here are going to make up the beginning of my scientific notation. So I'm going to count. I'm going to move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. By moving it 11 spots, I get 5.75. Again, times 10. Now this time, because I moved it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times to the right, this is going to be a negative 11. And so the negative 11 tells me that the zeros are coming before the number. What if I had a number like 0.0025? Well, again, you can move that 1, 2, 3 times. 2.5 times 10 to the negative 3. Again, if I had a number like 0.00012, 1, 2, 3, 4, 5, 1.2 times 10 to the negative 5th. Okay, so let's talk about this scientific notation in terms of wave. So when it comes to a wave, and you saw in your last couple videos that a light wave in particular, which is what we're studying, can act like a particle or it can act like a wave. So we're going to focus on light as it acts like a wave. And this is a very basic light wave. And as you saw in your video, you can talk about light having a wavelength, which is this symbol here. So this is wavelength. And it represents the distance between two identical parts of the wave. We can also talk about the frequency of a wave. Frequency is represented kind of like a cursive F. This is frequency. And frequency is the number of wavelengths that pass a point every second. So wavelength is generally measured in meters. Frequency is measured in hertz, and hertz means per second. So if I said I have a frequency of 5 hertz, that would be 5 wavelengths per second. Now the reason we brought up all the scientific notation stuff is because the frequency of light waves is very high. So we need to look at really big numbers, and for wavelengths we need to look at really small numbers, so scientific notation comes in handy. Now the other thing that hopefully you see in your worksheet is that there is a negative relationship or an inverse relationship between frequency and wavelength, which basically means that as the frequency goes up, the wavelength goes down. Now this is for light. Okay, now there's a reason why that works, and that works because the speed of light, no matter what type of light I am talking about, is constant. It is 3.0 times 10 to the 8th. That could be for radio waves, gamma waves, any color visible light, red, orange, yellow, blue. It could be for microwaves, infrared, you name the type of light. Light moves at that speed, which, by the way, is this number here. So it'd be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. 1, 2, 3. So that is 300 million meters per second. Now to give you some perspective with what that speed means, if I was to put this in terms of a football field, it would be the equivalent of moving 3 million football fields every second. And so if you took 3 million football fields, laid them end to end, and counted to 1, light can travel that fast. So we're talking about an incredibly fast moving thing. But because the speed is constant, if I adjust the wavelength, the frequency will adjust in the opposite way. And the way that we prove that mathematically is that we say that the wave speed is equal to the frequency times the wavelength. All right, so let's see if we can apply this to more of a real world type problem here. So it says Sachi is rocking her favorite radio station, 102.3 FM. The station broadcasts signals with a frequency of 1.023 times 10 to the 8th. So that number should be 1.023 times 10 to the 8th hertz. The radio wave signal travels through the air at a speed of 2.99 times 10 to the 8th meters per second, which for our class we're going to call 3.0 times 10 to the 8th. Determine the wavelength of these radio waves. So what I like to start with is identifying what I know. Okay, so my knowns are as follows. I know the wave speed is equal to 3.0 times 10 to the 8th meters per second. I also know the frequency is equal to 1.023 times 10 to the 8th, times 10 to the 8th hertz. So we are trying to find wavelength. So here's my knowns. My unknown is wavelength, and I know that I have the equation wave speed is equal to frequency times wavelength. So my next job is to plug in what I know. So now I plug in what I know. So wave speed becomes 3.0 times 10 to the 8th meters per second, which is equal to the frequency, 1.023 times 10 to the 8th hertz times wavelength. So now it's no different than solving this problem. 5 equals 2.5x. You would divide both sides by 2.5 and x would equal 2. So here we need to divide both sides by 1.023 times 10 to the 8th hertz. 0.023 times 10 to the 8th hertz. All right, now to do this on a calculator, everybody's calculator is a little bit different. Oops, let me shrink this up a little bit. Grab the browser here. So, sorry. So in my browser, you can see that there is a calculator that I'm trying to get to. It's not working very well, but on the calculator, let me move that out of the way. There we go. You can see that there is this exponent button. So if I want to do 3.0 times 10 to the 8th, I type in 3.0, I hit exponent, which gives me the E. On your calculator, you might have a button that says 10x or E. You might have to hit the second button. This is the best one. It'll look just like this. So we have 3.0 times 10 to the 8th. Let's see if I can get this to work now. Times 10 to the 8th divided by 1.023 e to the 8th equals. Maybe. Come on. There we go. 2.93. So, get rid of that. We can bring that back here. And we said now that the wavelength is equal to 2.93. And now we need our unit. And if you remember, I told you that hertz is also a per second. So the seconds will cancel out with the hertz, and I'm left with meters. So 2.9 meters. So if you picture that radio wave that's getting to your car's antenna looks this long, that means the distance from here to here is 2.93 meters, or roughly 9 feet. From here to here is another 2.93 meters. And there is 1.023 times 10 to the 8th of these passing by your car's antenna every second. And so it's moving incredibly fast. Now you can solve for any of these problems using this equation here, plugging in your knowns, and solving for what's unknown. You are always, for light, going to use the speed 3.0 times 10 to the 8th. So I hope this helped. Go ahead and check out your worksheet and check the answer key if you need to make sure you're doing it right.